Okay, good afternoon, everyone. All right. Okay, so today we continue, right? So for 3.3, there is a electromotive force, right? Okay, so electromotive. Wait for a moment. Yeah, close. Hi, okay, how you doing? All right. So we continue. Right, so electromotive force. So we already learned for 3.2 resistance, right? So we already finished about resistance. Okay, so now we move to electromotive force and also the internal resistance. Okay, so the diagram shows a simple torch and its circuit consisting of a cell, switch, and also the light bulb, right? So when the switch is closed, right, the circuit is complete. The bulb lights up, showing that the current flows in the circuit. Okay, so the flows of current is the flow of charge. What caused the charge to flow in the electric circuit? So this one, of course, if you switch on the circuit, right, then the current will flows, then the bulb will light up, right? So what caused the charge flows in the electric circuits? Okay, so this one, remember I told you, right, about the energy loss, right? The resistance should be high, then the energy loss will be increased, but then the energy will change into the heat and also the light energy, right? So this here, battery is a source of electrical energy which move the charges around the circuit. So this is a source of electrical energy that will move the charge right around the circuit. So the battery convert the chemical energy stored. Okay, so inside the battery, of course, you know there are electrolyte, right? So that one is consists of the chemical energy. So that chemical energy will be turned into the electrical energy. So the energy supplied move 1 coulomb of charge in the circuit. So mean 1 coulomb of charge, right, is moving around the circuit. Okay. And then the each 1 coulomb of charge that flows through the battery will receive electric potential energy to move in the circuit. So every 1 coulomb of charge, okay, that flows through the battery inside the battery will receive, right, will receive electrical energy, potential energy to move in the circuit, right? So there will the charge will move, okay, to complete the circuit here. So therefore, work is done by the battery in driving the charge around a complete circle. So it means there is work done, okay, by the battery to drive the charge, right, to around the circuit to complete, actually to complete the circuit, right? So the battery that provides electrical energy is source of the electromotive force. Okay. So we move to the next part, electromotive force. So EMF. So that is the EMF is stand for the electromotive force. So EMF is the total work done by a source in driving 1 coulomb charge around a complete circuit. So means if you have a circuit, right, and the 1 coulomb charge, right, the work done that to move that 1 coulomb charge, right, 1 coulomb charge around the circuit, okay, we call it as the EMF, right? So how much the energy that we use, okay, to to move, right, to move 1 coulomb of charge, 1 coulomb of charge in the whole circuit to complete one circuit, means from positive to negative, right, usually. Okay, so the EMF is total energy supplied to drive 1 coulomb of charge around a complete circuit. So how many energy you use, right, to move 1 coulomb of charge, right? So this is the formula for the electromotive force. Okay, so E over Q. Okay, so the electromotive force is the energy supplied by divided by the total charge flow. Okay, so how much the energy being supplied and how much is the total charge flow. So E divide by Q. Okay, so Q is one, you can use this formula. That is Q is equals to I over IT. Q is equal to IT or Q is equals to NE. So this is the two formula, right? So N is a number of charge, E is the charge of electron, and I is a ampere, of course, the current. T is the time in second. So this is a formula if you want to find the Q. So let's say if the question come up, you can use this formula to find Q, right? So E over Q. Then the unit is JC negative 1 joule per coulomb. Okay, to compare between the EMF and the potential difference. Okay, so in the remember when we doing the Ohm's law, right? So usually the voltmeter we put it parallel to the constant wire. Okay, that one is for Ohm's law. Okay, we put the voltmeter parallel to the constant wire. Okay. So, but for the EMF, right? If you want to calculate the EMF and also the potential difference, you put the voltmeter parallel to the battery. See? You put the voltmeter parallel to the battery. Okay. Let's say just if you use the constant wire just now, let's say if I put this one as constant wire, right? So you put the voltmeter parallel to the constator wire. This one is for the Ohm's law. Or you want to investigate about the factor affecting resistance, right? So that one also we put the voltmeter parallel to the constator wire. But for this one, for the EMF and also the potential difference, okay. So this one we change it to bulb. Okay, the constator wire we change it to bulb, and also the voltmeter we change to the parallel to the battery, right? So it says here the switch S is at the open position, mean it's switch off. So if the switch on means there is no current flows in the circuit, right? Right? There is no current flows in the circuit because the switch is off, right? But there will be a reading, okay? There will still be a reading for the voltmeter. So you see the diagram here, okay? Even the switch is not is switched off, right? There is a reading, okay, for the voltmeter. There is a 3 volt. So where does the 3 volt come from? It's actually the voltage or the EMF for the battery. So mean that one is for the battery. Okay, you can see even the switch, right, is open, right? The switch is open, okay, but there is still reading for the voltmeter. So, and the current is of course zero, right? Because there is no current flows in the circuit. But the voltmeter still shows the reading. So where does the reading come from? Actually, the reading is for the battery. So 3 volt is actually for the battery. Alright, so this is called as the EMF of the battery when the switch is open. Okay, right. And then if the circuit is we switch off the switch, right? Sorry, we close the switch, right? So now the current flows, right? So when the current flows, right? So let's this okay. So this one when the switch S is open. So you can see the mental light off because there is no current flows. Okay, and the emitter is 0 ampere, right? Because there is no current flows. But the reading of the voltmeter shows 3 volt, right? So that one when the switch S is open. Okay, but then when the switch S is closed, right, the mental will light up because now the current flowing in the circuit, right? And the emitter, there's emitter reading, of course, because now the mental is light up, so means there is a current flow, so 0.2 ampere. But you can see the voltmeter reading is dropped, right? Now it becomes 2.7 volt. Okay, 2.7 volt, right? So then this actually this come they're doing the experiment and they take the picture, right? So what is the EMF of the battery? That one is 3 volt. So you have to remember the EMF is when the switch is open, means there is no current flows in the circuit, but the voltmeter still show the reading. That means that is for the EMF for the battery E, right? So what is the potential difference across the bulb when the switch S is closed? Okay, so when you close the switch, right? Now the current flows. So the voltmeter will give the reading. The value is V. That one is for the switch. For the bulb means the voltage that flows through the bulb is 2.7. Okay, so this one is E, right? This one the value is for V. Okay, because later you will learn the formula for the EMF. E is equals to V plus I R, right? Okay, what is the change in the energy when the bulb lights up? Of course, electrical energy to light and heat energy. So what is the quantity of electrical energy released by the bulb for 1 coulomb charge that flows through it? So the potential difference is 2.7, right? 2.7. So 2.4 of electrical, this one is actually 2.7, right? Not 2.4. 2.7 of electrical energy emitted to the bulb for 1 coulomb of charge. So it means that every seconds, right, there will be 2.4 joule of electrical energy emitted to the bulb. Okay, so what is the quantity of electrical energy that is required to 1 coulomb of charge flowing through the dry cell? So the EMF is 3 volts. So 3 joule of energy is supplied, okay, to move 1 coulomb of charge from a battery. Okay, so mean this one, they say you want to take out 1 coulomb of charge, okay, from a battery, you need 3 joule of energy. Okay, so that's the meaning, right? So if you want to take, let's say, 1 coulomb of charge. So let's say 2 coulomb of charge means you need 6 joule of energy. Okay, so to move the charge from the battery, right? Okay, so this is the comparison, okay, for the open circuit. Open circuits mean the switch is open, right? Means there is no current flows, okay? And the voltmeter reading is 3 volt. So this one is actually the voltmeter reading across the battery when switch is open. So the EMF is 3 volt, okay? But then if you close the switch, right? Now the current flows in the circuit, so the voltmeter will decrease, okay, if the switch is closed. So let's say it become 2.7. So means the potential difference across the bulb is 2.7, or we call it the value of V. Okay, so this one is for E. Before, when the open circuit mean when the switch is open is E. When the switch is closed, okay, the potential difference is V. Okay, you need to know the difference. Okay, so I'm just skip. Right. Okay, the comparison between EMF and potential difference. Okay, so the total work done, okay, the electromotive force is the total work done by a source in driving 1 coulomb of charge around a complete circle. Okay, so this one, it says a complete circle. You can see the difference here, complete circle, and this one is only between 2 points, right? Between 2 points. Remember, the one I said about the bird, right? The bird, the distance between the legs, okay, between two birds is very small. So means the potential difference is smaller. Why it becomes smaller? Because the work done means from the, let's say, from the left leg to the right leg, right? So the distance is very small. So means the work done to move from left leg to the right leg, right? Is very small. Okay, so the work done is very small. So the potential difference is small, right? But if for the electromotive force, you need to have the complete circuit, means from positive to negative. So it's a complete circuit. But for the potential difference, is only from 2 point only. So let's say from here to here. Let's say, as I said, from point A to B. That is a potential difference. Okay, but for the electromotive force, it means for the whole circuit from the positive to negative. So how many work that been done to move from positive to negative, to move the 1 coulomb charge from positive to negative, okay, for the whole complete circuit. But this one, how many charge, how many energy you need, or how much work is done to move from A to B. That is a potential difference. It's not for the whole circuit, only from point A and B. Okay. All right, so that is the difference between the electromotive force and also the potential difference. Okay, right. And this one we already know lah. If electromotive force mean when the no current flows in the circuit, the voltmeter still give a reading, right? That means the reading is for the EMF. But when the switch is closed, right, then the voltmeter give a reading, but you can see there is a drop of voltage. That one is a V. Okay, so the unit actually the same, right? Volt. Okay, so here you can see if you buy a battery, right? So this is the example lah. Okay, so 1.4 joule. What does it mean by 1.5 volt, right? So usually this one size 2A is 1.5 volt. So the 1.5 joule energy is need to move 1 coulomb of charge around a complete circuit. That means that is for the EMF, right? You see the complete circuit here. So it means for the EMF. So mean if you want to complete one from positive to the negative, you need 1.5 joule of energy to move a charge of 1 coulomb. Okay, this is the example, right? Okay. Now, to study the effect of internal resistance on a voltage drop. So we do the, let's say we do the experiment, and you see when the switch is open, the reading is 3 volt. When you switch is closed, then it's dropped 2.7. So what is actually happened there? Okay. Right. So why should a new dry cell be used in this activity? Okay. So mean you need to change, right? To change you need to use the new one. Okay. So you cannot like take the one that already been used, because we want to make sure that the EMF is 1.5. Okay. So to make sure that EMF for both batteries are equal 1.5. Okay, so which brand of dry cell experience greater voltage drop? So you can see here when the switch is open, both of it give you 1.5 volt. So this is actually the brand of the battery lah, Duracell and so Energizer. So we compare these two brands. So the voltmeter when the switch is open means the electromotive force, right? So the electromotive force for Duracell is 1.5 and Energizer 1.5. So they give the same reading. Right, but then when we switch off the when you switch the switch is closed, now means the current is flows, right? So when the current is flows, we can see the voltage drop, right? So for the Duracell it dropped to 1.4. Okay, while for the Energizer it dropped until 1.3. Okay, so how much is the voltage? Okay, the voltage that lost is 0.1 and this one is 0.2 volt. That is the voltage that dissipated. Okay, 0.1 and also 0.2. And remember this the connection of the uh voltmeter, right? When you want to investigate the internal resistance or the electromotive force, remember again this one the voltmeter have to be parallel to the battery. If for the Ohm's law, this one they must be parallel to the bulb. Okay, so that's the mission, or using a constant wire. Okay, so it says here, which brand of the dry cell experience a greater voltage drop? Of course, the Energizer lah, 0.2. So why there is a difference in voltage drop between the two dry cells? Explain. Okay, so why does the voltage drop? So voltage drop is different because the internal resistance are different from for both brand. So actually, this one is actually connected, okay, to the chemistry, right? So you already learn to make a simple, I think electrolyte, right? Okay, the one that the anode goes to the I think anode goes to the anode charge, right? Anode goes to the negative plate and the cathode goes to the positive, right? So you can see there's a moving of charge there. So actually that one is using that one for the battery. So what happened when the voltage drop? So means the voltage drop means the energy, there be energy being used, right? Its energy is lost. So why the energy is lost? Okay, so it's actually lost because of the moving charges in the electrolyte. Because in order for the anode for the charge, negative charge and the positive charge to move to the anode and the cathode, they need energy, right? So that's why the voltage is dropped, because you need to move inside inside the battery. Also they got the electrolyte, then electrolyte also they got the charges, so they need to move the charges, right? So that when they're moving the charges mean they need energy. So that's why it's dropped, because the energy is being used to move the charge, okay, inside the battery. Okay, so the voltage different, drop is different because the internal resistance are different for both brand. So each brand of dry cell has different type of electrolyte. Okay, so the cell with high internal resistance will have the higher voltage drop. So internal resistance is caused, okay, by the moving charge in the electrolyte. Okay, you are learn and not cathode, that one, right, for chemistry. So that need energy. Okay, so when that need energy, so that's why there is a voltage drop. And you already know voltage drop is actually the work done. Work done means work is actually equals to uh is work done is actually W is equals to Fs, right? So means there must be energy, right? Being using. Okay, so that's why they got the internal resistance there. Okay, so means the internal resistance for the energizer is higher. That's why is 0.2. Means it's required a lot of energy to move the charge compared to the Duracell one. So the Duracell doesn't need that much of energy to move the charge, okay, in the battery. But in Energizer, they need a lot. So that's why the Energizer is higher, right? The voltage loss is higher. Okay, internal resistance. So this one, this is I told you just now. Internal resistance of the dry cell caused by electrolyte in the dry cell. So the SI unit for the internal resistance is ohm. Okay, as long as you call it as a resistance, yes, it's ohm, in ohm. Okay, so the internal resistance causes loss of energy in dry cell as work has to be done to move 1 coulomb charge against the resistance within the dry cell. So this one I said just now, right? To move the 1 coulomb charge inside the battery itself, right? So that is actually the internal resistance. So the potential difference across the dry cell terminal to be less than the EMF when the current flows in a complete circuit. Okay, because the energy also need to be used to move the charge, okay, inside the battery. So that's why the energy drop. If you switch off let's say you switch off, right, the circuit. So when you switch off the circuit, I mean there is no moving charge, right? When you switch off the circuit, there is no moving charge inside the battery. So the battery will give the reading of EMF, because there's no charge moving. So it's 3 volt. But then when you switch on the circuit, right, now the charge is start to move. So when it start to move, mean it's required energy. So when you move, right? So mean they require energy inside the battery itself. So it will consume, right? It will consume the voltage. So that's why there's a voltage drop. Okay, because that one is to move the charges, right, inside the battery itself. Okay. All right. So this is the formula. Okay. I just teach you the formula lah. You need to know how to derive it. Okay. So write an equations. E is equals to V plus IR. And V is equals to IR. We can factorize it. So we can get E is actually equals to IR plus R. So what is R? R is actually the resistance, the effective resistance of the circuit. R is the internal resistance of the battery. Okay. And E is the EMF. Okay. So when the voltage, when the switch is open. Okay. And V is the voltage when the switch is closed. So you need to know the difference. And I, of course lah, the current flows. Okay. That flows in the circuit. So experiment, this one I will. Let's try to see
the A-level physics practical to find the EMF and internal resistance of a battery. So batteries provide an EMF, that's electromotive force. You can think of that as the total voltage that the battery can output. However, batteries are not perfect conductors, so they have a little bit of resistance inside of them. So we can model a battery as a perfect battery with a little resistor inside as well, and we're going to call that the internal resistance. What we want to do is hook up a battery to just a load resistor. It's a good idea to have a variable resistor so you can change it because we want to change the current flowing through the circuit, therefore the current flowing through the battery. We want an ammeter in series with the battery and resistor as well. So what I'm going to do is change the load resistance. So this is my load resistance here. You might have some.
So this one actually the replace it. Actually we use bulb, right? We use bulb, but this one they put the load, right? They use a rheostat. Rheostat as a resistor. Actually in the lab we use a bulb because we want the resistance to be constant.
So even though the battery says 6 volts, there's not going to be 6 volts available to the circuit because some of that
this one is
the sure enough, my
to replace the voltmeter and ammeter. That one is a multimeter. Okay.
That shows that some of the 6 volts EMF from the battery is being lost in the.
Okay, this one, the black one, this one you call it as a multimeter. Multimeter is actually the one it can function as the voltmeter, ammeter, okay, and it has a lot of scale of range, right? So that's why we call it a multimeter, and also they can add also as a resistance, right? So this one we got, but I think only like one or two because it's quite expensive. Okay.
Battery.
So this one we add as the voltmeter, and this one we add as the ammeter.
By reducing the resistance in the circuit, see what happens. I now have a current of 0.
So this one voltmeter, this one is ammeter.
And therefore flowing through the battery.
So you can see because
the terminal PD is now 5.37 volts. So even more of the EMF has been lost in the battery. I'm just going to get my PDs for 0.30, 0.40, and 0.50 amps as well. And so here are all of my results. As we can see, as the current increases, the terminal PD goes down, which is what we expect. Let's draw a graph of that, where we have terminal PD on the y-axis and current on
so this is the graph.
Now, if there was no internal resistance, then we should just have a flat line. But because there is internal resistance, the more current we have flowing through the battery, the more of that total PD, as the EMF, the internal resistance takes up. So what we can do is extrapolate this line back to the y-axis.
Okay, so this one, they change the current, right? So when they change the current, they observe the voltmeter. So actually when the 0.1, okay, that the voltmeter gives you the reading of 5.6. Okay, this is actually the roughly 1.6 something. Okay, when 0.2 it gives 5.4. When 0.3 is 5.2. So means when the current is increased, right? When the current is increased, right, the voltmeter reading is also decreased, right? The voltmeter reading is decreased, right? So because there will need lot of energy, right? Because now the charge is moving rapidly, so mean there's lot of energy. So mean the value of the voltmeter will be decreased, right? So this is they say the graph, right? So this is they say the graph. So this one is different from the graph that you learn in Ohm's law. Ohm's law, you know that the voltmeter is directly proportional, right? So it will pass through 0, then it go up, right? It increase. But for the V against I, for the internal resistance, you can see the graph is going downward. Means it's decreased linearly. So let's say if this come out in the exam. So what is the relationship of the graph? Decreasing linearly or linearly decreasing. Okay. So the value is decreasing but it's linearly. Okay. Then you got this one, right? The result. So when you pass through, okay, let's say you make this line longer. Okay. When you make this line longer, then it will intercept at one point at y-axis. So this one we call it as E. This one is actually E. The intersection of the y-axis is E, means the electromotive force, okay, and the gradient, okay, and the gradient, okay, so the gradient is actually equals to the R, internal resistance, okay. So later you will learn. Let's say E is equals to V over IR, right? E is equals to V plus IR. Okay. So if we compare with Y is M X plus C. So your E is Y, right? Y axis. Okay. Your X is actually here is I, right? Yeah. And your M is actually equals to what? R. M is the gradient. So your gradient is actually equals to the internal resistance. You compare the equation just now, relearn E is equals to V plus IR, right? So if we compare, the M is actually the R, the X is as this is your I, right? So this is your I, okay? And your C, okay, your C is actually the V, okay? No. Actually, it's like this. Wait. I arrange first. This one, it should be the C is E. Okay. So we have to arrange the equation first. Right. So this one, C is the E and the V is the Y. This one. Okay. So means C1 become, E is negative, of course lah. Because, wait. I arrange, right. So Y is equals to MX plus C. Okay. So means this one, let's say I put this is a V. Okay. So I change the E minus IR, right? Okay. So Y is your V, okay, and M is your I, negative I, of course, because the gradient, right, is decreasing. Okay, the graph is decreasing, so the value of the gradient is negative. Okay, and your R, sorry, your X is your I, and your C is the E. Okay, so you need to compare because this one can come out in the paper 3. Okay, the practical one. Okay, so they give you Y is equals to MX plus C. Y is actually V. Okay, and your C is E. Okay, and your M is a negative IR. So this is your X, and this is the gradient. Right? Okay, so this one I already told you the gradient is we compare, right, the equations. Okay, so I think we can do this one as the, but I need to find the bulb because we don't have bulb, the bulb holder. We don't have the bulb holder. That's why we cannot do that experiment because we need to use the bulb as the resistance because the resistance needs to be constant. So it's better for use to the bulb, right? But maybe I will try to find someone else, something else to replace the bulb. Maybe we can use the constant wire as the resistance. Okay. Or let's see lah. Okay, I try to modify the experiment first. Okay. So if the straight line is the extroverted until it cut the vertical axis V, okay, so this one is E, right? I just told you just now, and the gradient is actually equals to R. All right. So it says this next one is to study the effects of the connecting dry cell in series and parallel. So what happen if you put the dry cells in series and also the in parallel? Okay. So let's say if I have a battery here, okay, I put it parallel to each other. Okay, and the other one is series. Okay, so we compare, right? So we compare here. So for the E of course lah must be same, right? For the voltage, right? So if they say is the DGE is 3 volt, this one also should be 3 volt. Okay, and then if you see here, when you put it in series, right, the voltage drop 2.7. But if you put the dry cell in the parallel, right, it become 2.9. And this one actually we can use the one that we learned, right? When the resistance in series, is actually you just sum up all the resistance. But if for the parallel, you put 1 over R equals to 1 over R1 plus 1 over R2, right? So of course the resistance must be lower for the parallel circuit. So same also for the battery. Okay. So for the battery, if you put it in the parallel, the internal resistance is lower. Okay, compared to the series. So that's why the voltage drop also will be lower in parallel because the resistance, the internal resistance inside of the battery also become lower. So which arrangement of dry cell produce smaller effective resistance? So the arrangement in parallel produce smaller effective internal resistance. The current is bigger. Okay, because of the smaller internal resistance. So mean you don't need a lot of energy to move the charge inside the battery. So the currents can that produce can become higher, right? Okay, so this is actually the the cell drive cell, right, connected to the series, and this one connected to the parallel. So just now I said, right, if you series R plus R plus R per R, so you get 4R. But this one over R plus 1 over R plus 1 over R plus 1 over R, you got 4 over R, right? So then you cross multiply, actually your R is divided by 4. So you see this one 4 times R, and then this one you just divide by 4. So this one can reduce the internal resistance inside the battery if you put it in parallel, okay, compared to series. Okay, so now we need to learn how to solve the problem. Okay, so diagram shows a cell with EMF and internal resistance 1 ohm is connecting to a resistor of 4 ohm. What is the reading of the voltmeter when it's connected across the 4 ohm resistor? So they give you the E already. So we use the formula E is equals to V plus IR. Okay. So V is equals to IR, right? And then they give you E is 2. Okay. Then you need to find V, right? You need to find V here. Okay. And the internal resistance, they give you 1 ohm. Okay. Teacher, there is no current given. Yes, you can use V is equals to IR here. So your V is actually, this is 4, right? This is 4. The current is I and the resistance is 4. So the V is equals to IR. It's connected with internal resistance 1 ohm. EMF is connected to the resistor 4 ohm. What is the reading of the voltmeter when it's connected across the? When you want to find the V here. So V is equals to IR. So V is actually I is equals to 4, right? Okay, so we need to find the equation this one first. So if I put E is 2, I R R plus I, so 5I. Okay. So E is I R plus R. So E is 2, right? So I we don't know. Okay, and then your R is 4, your R1 is 1, so 2 is 5I. Okay, so I is equals to 2 over 5, so 0.4. Alright, 0.4 ampere. So we don't use this one, we use another one, that one that already derived from here, because we don't know the value of V here. Sorry, I R. Okay, so 0.4 ampere. Okay, then after that we use V is equals to IR. So VI you already know 0.4, your R is 4, so you just time you got 1.6 volt. Okay, and the next one, okay, the bulb is M is connected to a battery by a means of a switch. So a voltmeter is also connected across the battery. So when the switch is open, means the current is not flowing. The voltmeter reading is 6 volt. So this one should be E. E is 6 volt. So when the switch is closed, the voltmeter reads 4.8. So mean V is 4.8. Right. So the question said, what is the EMF of the battery? 6 volt. Right. Okay. If the resistance of the bulb M is 8 ohm. So 8 ohm. What is the current passing through the M when the switch is closed? Okay. So we have E is equals to I. Okay. The V we already got here. Right. And then the resistance. Okay. Let's find the I. R the internal resistance V plus IR. A, so your E is 6, your V is 4.8. You need to find the I. The I is to find, and then the general resistance. Okay, so for V is 4.8. So we just use V is equals to IR actually. So your V is now given 4.8, right? 4.8, and then your I you need to find, then your R is 8. So I is 4.8 divided by 8, you got 0.6 ampere. Yeah. Okay, 0.6 ampere. That one don't need to use the E equals to V plus I. Just use V is equals to IR. Okay, they give you the value of V already, 4.8. Okay, and then R is the resistance of the bulb. Okay, 8, then 4.8 divided by 8, you got 0.6 ampere. Okay, find the value of the internal resistance R of the battery. So this one, we can use E is equals to V plus IR. Okay, so your E is 6, V is 4.8, your current is 0.6 R. So 1.2, okay, this one change here, 1.2, 0.6 V, sorry, 0.6 R, so R is 1.2 divided by 0.6, so you got 1.2 divided 0.6 is 2. So your R is 2 ohm, the internal resistance. Okay, so just use that formula. Okay, next, when switch S is open, the voltmeter reading is 1.5 volt. Okay, so when switch S is open means there is no current flows. So 1.5 volt is the E value. So when the switch is closed, the voltmeter reading is 1.35, so means 1.35 volt. And the ammeter reading is 0.3 ampere. Alright, then calculate the EMF. So EMF already given there, 1.5 volt. So the internal resistance, okay, we use the formula E is equals to V plus IR, right? So your E is, here is 1.5. Your V is 1.35 plus I is 0.3, and you can find your R here. Okay, so you will get 0.5. So this is, you can just, this one become minus and divide by 0.3 later. So how about the resistance? Okay, so we use a V is equals to IR. Okay, so we already know the value of V is 1.35, right? Okay, and then your I is 0.3, so you can find your R. Okay, so you will get your R is 4.5 ohm. Okay, so it means you can use these two formula. E is equals to V plus IR, and also V is equals to IR. That one is for Ohm's law. Okay, or this one you can change it. They say they didn't give you any reading of the voltmeter. When the switch is closed, you can use E is equals to I R plus R. This one, if they didn't give you the value of V, means the voltage, the reading of voltage, right, when the switch is closed. If they give you this one, they give you E, they give you V, means you use this one. If they didn't give you any value of V, you use this one. Okay, but must have current. No? Okay. Alright, so diagram shows an arrangement of a dry cell in 3 circuits. Okay, EMF of each dry cell is 1.5 volt and internal resistance R is 1 ohm. Calculate the current flow in each circuit. Which arrangement of the dry cells, okay, give a greater current? So you have to find one by one. Alright, so for the first one, they give you already the E is 1.5, right? Okay, and the internal resistance is 1 ohm. Okay, and this one you can see they give you R is resistance is 9 ohm for the circuit. Alright, so the first one, E is equals to, this one is the formula, and they change it to I is equals to E divided by R plus R. Okay, so your E is 4.5. Why 4.5? Sebab one battery is 1.5. So if 3 battery means 4.5. Okay, this one got 3 batteries, right? So 4.5. So your R is 9. Okay, and the internal resistance is 1 ohm because 3 battery. So means 1 ohm plus 1 ohm plus 1 ohm. So 3 ohm. So we get the value of the current 0.375. Okay, for B, right, because this one is a parallel, right? So means the internal resistance here, you need to find, you want to find the effective resistance for the battery. So 1 over R, right? So 1 over R plus 1 over R, 1 over R, right? Uh, so it become 1 over, this one, the internal resistance is 1, right? 1 over 1 plus 1 over 1 plus 1 over 1. So you get 1 R over R is 3 over 1. 3 R is equals to 1. R is 1 over 3, right? or 0.33. Remember, no fraction, right? So 0.33. So this is the internal resistance for this one. Okay, so again we use the same formula. So your E is for 1.5, right? Because the now is the voltage, right? The voltage must be same, right? For the parallel. Remember, for the parallel the voltage is same, 1.5. Okay, so that's why it become 1.5 here. But this one, the E is 4.5 because it's series, right? Series, the voltage mean you need to add all the voltage, right? 1.5 plus 1.5 plus 1.5. This one, no. Okay, parallel, the voltage is same, right? So 1.5 and then equals to 9 plus. So this one 0.33 I got from here. Okay, so and then you just calculate, then you got 0.161. Okay, and then for C, right? For C, this one, okay, this one you need to solve this one first. Means 1 over R plus 1 over R, so 2 over R. 1 over 2 over 1, right? So 1 over 2. So means your R, this one, R is 0.5. Okay. The R is 0.5, but you need to add this one. So 1 plus 0.5 is 1.5. This one, you calculate the internal resistance for this one. Parallel, right? 1 over R, 1 over 1 plus 1 over 1. So you got 1 over 2 means 0.5. So 0.5 add this one, add by 1 is become 1.5. Okay, this one is just like you solve the parallel circuit, series circuit, right? Okay, you combine this one two first, then you combine it, now it becomes series. Okay, so 1.5, then again, you use the same formula. Okay, so your E now is 3 volt. Okay, so 3 volt because this one is 1.5. Okay, the voltage is same, 1.5, and this one is 1.5. 1.5, 1.5 is 3 volt. Okay, and then 9 plus 1.5, you got 0.286 ampere. So which one has the greater current? Of course, the one that we use, the A. Even the effective resistance for the B and for the B is lower, right? Right, for the B is lower because we divide, right, 1 over R. But however, the currents, right, that actually we want to, of course the current must be higher lah, because if they say you want to light up your bulb, right, of course you not want to be higher, so it can bright, right, the light produced, right, can be higher, right? So the energy is higher. So that's why you put it this way. We didn't arrange our battery like this in the lab, also in the experiment. And also one thing, if you put it like this, whatever if you put it like this, the voltage is same, right? So what's the point? If you put it like three battery, you only get, if you put three batteries parallel, right, you only still get 1.5 because the voltage is same. So what's the point, right? Because we want the higher voltage, right? So the voltage higher, the current also will be higher. But if you put it this way, all the current, the voltage is same, 1.5, 1.5, 1.5. So the voltage flows also in the circuit also 1.5. So there's no change. What, there's no use, right? But this one 1.5, 1.5, 1.5, you can have 4.5 volt, right? So when it's higher voltage means higher current will be produced based from the V is equals to IR. So that's why we put the battery in the series one. Even we know that internal resistance, if you put it in the parallel, okay, the battery is parallel, the internal resistance will be lower. Okay, but no, yeah, because we want the voltage actually. It's the same voltage. So there's no need, right? Okay. I think we can go to the questions. We still have like 10 minutes. Mm, okay. I just discussed lah. I mean like for 5 questions, then we stop. So we finish for the electromotive force. So the next one, and the next week we can go to 3.4. Means in this class lah. Say I think for S for M for K already finished 3.2. Okay, now we're going to 3.5, and also the exam until 4.2. Okay, 4.2 means the electromagnet, right? Okay. So tutorial 7.4, what is the electromotive force? So electromotive force is actually to compete a circuit, not like 1 point to 1 point. That one is a potential difference, right? I already told you just now. Okay, so the work done by a source of energy in driving 1 coulomb of charge in the complete circuit mean must from positive to negative. Okay, which circuit can be used to determine the electromotive force of a battery? So remember, voltmeter must be parallel to the battery. So which one parallel to the battery? So of course this one. Okay. So the answer is C. Okay, which of the following graph relates the reading of ammeter and the voltmeter in the figure below? Okay, so you see the voltmeter, right? So this one we already know because this is the topic for electromotive force. So of course you know the graph should be downward. But they say in the exam, right? So we don't know, right? Which topic is this one? Okay, you see the voltmeter. Where's the voltmeter? When the voltmeter parallel to the battery, alright, that one is for the electromotive force. Mean the graph will go decreasing linearly. Right? So this one, the voltmeter is parallel to the battery means of course that's this one, right? D. Okay. This one if the voltmeter parallel to the constant wire or constant wire. You cannot use bulb because bulb is a non-ohmic conductor, right? Okay, for this one, the three resistance, the last one, after that I will stop. So the three resistor with the resistance shown are connected to a battery. The electromotive force, the internal resistance of the battery are E and R respectively. So which of the following statement is true? So E equals to the reading of voltmeter V1 plus V2. Okay. And A1 is equals to A2. Okay, reading of voltmeter V1 plus V2. Yes, V1 and V2. Which one is V1? Okay, so V1 and V2. Yeah, if you add, you can get this one. Okay, and V1 is higher than V2. Is it the resistance is same? Yeah, they didn't mention so. Oh, no. Because this is R, this is 2R, right? Mean the resistance is higher for this one. Okay, so the reading of voltmeter is not same because they have the difference. Wait, I've tried to count first. 1/2R is equals to plus 1/2R, right? 2/2R. So 2R is equals to 2R. Okay, so means R is equals to 2R/2. Sorry, yeah. So you can cut it off. So means it's same, right? It's same, right? 2/2R. So the resistance is same because they put it in the parallel. So it's same. So your R is same. So V1 is equals to V2. Yeah, and A1 is equals to A2. Of course, because it's series, right? So I think the answer is effective resistance of the circuit is 3R wrong. Okay. 2R plus R is 2R, not 3R. So the answer is, oh, this one got B, C, D. Okay. So A1 is equals to A2. The reading of voltmeter V1 is equals to V2. Actually, that one also correct, right? A1 is equals to A2 because that one is a series circuit. Okay. So the answer, I think this one A and this one is B and this one is C, this one is D. Because I don't know why it just circle this one, or maybe the answer is A, right? Okay, so number 4, the answer is A. Okay, if you calculate also, you can get the same one. 1/R, 1/2R plus 1/2R. So 1/R, 2/2R. 2R is equals to 2R. So R is equals to 2R over 2. So 1R, right? So it's same actually. Okay. Alright, so I think I stop until now. So we continue this one, the exercise during the class. Okay. So thank you, class.
Thank you, teacher.
Alright. Bye.